Hey guys, it's Professor Floyd here, and we are looking at OEH 5723 Homework Set 4. In this homework set, I've asked you to use the provided Excel spreadsheet on Desire to Learn D2L under Lecture 4, Homework Set, or Lecture 4, and then it should be, there should be two different Excel files. One is going to be instantaneous puff dispersion. So pull that one up, open it, save it onto your computer, however you want to do that. And that file, I'm asking you to model what the concentration of sulfur dioxide will be in air at 1 meter away from a puff that's released. So if that puff was released from a point source and it radiated outward in 360 degree, well, in a spherical manner, so point source radiation, then using two different diffusion coefficients, what does that concentration profile look like at 1 meter? And what's your interpretation of that? What are you understanding that to mean? So there's two tabs on there's actually three tabs on the Excel spreadsheet. One is going to be a graph that's already automatically grabbing the output data from the second tab. The second tab is the tab that you want to use, and it is labeled instantaneous puff. The third tab is instantaneous puff dispersion, which is not a terribly useful name, but if you click on that and look at the XY column, you'll notice, I click on it, the very first column, column A, is R parentheses meters. So the variable here is concentration with distance. This is not the spreadsheet tab that you want to use. You want to use the second one that's labeled instantaneous puff, and the variable in the A column is, or the output is time, and in the B column is concentration. So we're looking at concentration in time, and we have to specify up at the top what our distance is, what our R is. So I'm going to move the camera over to the back of my normal chair and see if I can't get a good screenshot here. Try to explain this to everyone. Alright, well that's not too bad. So if I make this bigger, then you can see the column headings here. We have dt, so the change in time, and this increment, if you click it, you can see it's 1 divided by 60. So it's dt in minutes, so we want 1/60th of a minute, also known as a second. So every second we want to get information with what's going on with the concentration. And so you can see there's a nasty little formula here, and this is the Excel input of this formula. So when you open it up, you're not going to have this formula already here. I went onto the slides and I just copied it out of the slides and pasted it here. I find it helpful for me to remember what equation I'm trying to build if I wanted to verify that this is correct. For your sake, you can just assume that this is correct. So you put in your time interval, in this case 1/60th of a minute, or every second. You put in your diffusion coefficient. So I, in the homework, asked for you to do this at 0.1 square meters per minute. And then here I asked you to do the distance as 1 meter. So I've already done input some of this. These values will probably be different when you grab it off of the internet, off of D2L. The mass that was released is 5 grams, sort of an instantaneous release. And then the molecular weight, I've already input this. It's 64.066. You can use 64, that's fine. I think if you don't change this though, it's input at something like 88. So maybe we were looking at benzene, or I don't know, previously. So you just put in 64.066. Get online and look it up, Nice Pocket Guide, or just somewhere on Google. So what we have is we have the time elapsed. So that's 1 second, 2 seconds, 3 seconds, 4, 5, 6, 7, 8. And then this is the concentration. And so this is being calculated by using these fields up here, and then the time as well. So you can go through that, but that is basically just this equation. So you'll also see that there's some things that have been done here for you. There's a 1 minute average. So just kind of what was the concentration average for the first minute? Well, so how did we do that? That's just the average of these first 60 cells here. So you can see them highlighted in blue, and you'll see it's the first 60 of them. So cell 64 and cell 5, so that's 60. All right, and then it's the same thing. A 5-minute average, it's just the first 300 cells, and then a 10-minute average for 600 cells. A 2-minute average, this one's just out of order. I think you get the point. The first 120 cells. So those are in ppm. So it just kind of gives you an idea, what's going on in time with this concentration. So I'm going to rearrange these real quick and put them in chronological order. So we can see, and this is all predicated on this distance of 1 meter away. So this is the average concentration at 1 meter, 1 minute, 2 minutes, 5 minutes, 10 minutes. So we can see it peaks somewhere here around 5 minutes, right? So all this is already input now. So we've got our time constant, we've got our diffusion coefficient, our distance, the mass that was released, and the molecular weight, which factors into the rate at which it will disperse. And then we go here and we click on this graph, the first tab, and look, it's already got these things input. So again, on this first tab, I brought in the formula just so that we would know what was being displayed. And so this is what you should see, something very similar to this. I'm going to delete this label because it's really not helpful or necessary. So at 1 meter, we can see right here that we have basically no concentration detected. And then our concentration really starts to rapidly rise. It peaks right around 2 minutes, and then it starts falling off. So basically we get a peak, and if you wanted to know when that peak was, you could identify it here and say, okay, what is that? And then maybe put some grid lines in or extrapolate it, 1.7 minutes. Of course, you've got your tabulated data. So you could go through here and you could find when does the concentration peak. And so we're up to the 140s, and now we're getting down to the 139s again. So you can do this manually. It looks like that's our peak right there. So at 1.667. So I interpreted that as 1.7. So graphs are really good for being able to get a quick glance at it. But of course I was off by 2 seconds, right? So so 140.5 is roughly our peak concentration at the 1 meter distance, and so concentration at 1 meter. It peaked basically at 145. So you could also do that graphically. You can click on this scale, you could right click it, format your axis, and then you could input the maximum and minimum and basically just zoom in. So I'm going to say my maximum is going to be 150 and my minimum is going to be 135. Okay, so my minimum 135, my maximum I'll do is 150, and now you can see, and then if I do my major units as 1, so now we can see, yeah, 140, it's basically 145. So if I wanted to zoom in even more, I could do that, make this 140 and make this next one 141, and so now I can really see that that was my zoom in, but I closed that out a little too early. I need to put my major units in. And so we can see that it's basically 140.47, 48, I don't know. So we can get an exact value off the tab data, 140.47, or we can, right, making sure everybody's seeing that, 140.47, and then we can also interpret it from the graph at 140.4, and then it's about 70% of the way between 0.4 and 0.5. So those are some things that you would see. Now I'm getting a little bit long-winded here, so I'm gonna real quickly jump to our next graph. So I'm just gonna put these back to auto. So this is where we started, and I'm gonna move that off to the side. So what I did is I actually clicked this. Sorry, close that. I clicked and then I copied and I pasted this into a Word document so I could have a screenshot. Now another trick that you could do is you could copy this tab down. You can just barely see my mouse in the corner, but you can take that tab, right click it, and then go to move or copy. Move to the end and create a copy. Or you can move it wherever you want. But so there's our copy down here. Down here is our copy, and we can rename this. We can just call this B because it's problem set B, and then maybe we want to describe that the diffusion coefficient equals 1 meter squared per minute. Okay, and then this one, we could rename this one if we wanted to A. D equals 0.1 meter squared per minute. Alright, so it doesn't seem to want to let me do the division sign. That's okay. I can just do the -1 notation. Okay, so now I've got this separate sign, and this separate tab, and so they're both identical tabs right now. And so I'm not going to get into the nuance, but you could basically copy this tab as well, copy the second tab, and make it so that the copy goes along with this new copy. Nonetheless, just click on this, paste it into a Word document, and then go in here, and we'll go back to our puff model, and all I've asked you to do is change your diffusion coefficient to 1 square meter per minute, and when you do, you get different values. We saw that these values changed. Now we don't have a peak here around 2 minutes. Our peak is in the 1 minute time frame. So let's look at our graph, and well, I'll look at this graph. And so you can see it changed real quickly. And so now we have a very different curve. Instead of it peaking out here around 2 minutes at 140 something, it's peaking at 1 minute. Now what's the concentration that it's peaking at? Anybody care to hazard a guess? Let's find out. So we will manually put these in at 140, and because I can see it's greater than 140, but I can also tell from experience. All right, so I can see it's less than 142. Let's try a 141. All right, so now we can see that it's peaking at about 144.7. My goodness, that is the exact same number that it was peaking at before. So it's doing the same thing. This concentration profile is the same, it's just the rate at which it's achieving those is different. So these are the things that I want you to describe. How is this plot different in its shape than the previous plot? And so this is what I did is I put these two into a Word document. And so this is the copy and paste. I changed my heading up here so that it was more descriptive, and then I changed my heading here so it was also more descriptive. So this is A, and this is problem B, and we can see they peak at the same concentration. We have differences in the concentration at the beginning, and again this one's interactive too. So you could change this. Let's see, what is that concentration in the first couple of ppms? So let's zoom in. Let's say our maximum 2 ppm, and our minimum 0, and our maximum 2. Let's see what that looks like. So and then let's amplify our time as well. And so I just clicked on this axis, and now the axis I'm formatting is the x-axis. And so the max time I want is 1 minute. And so we can see actually for a number of seconds we're getting absolutely no change in concentration. Let me put that back on auto. And now, so actually for about 0.2 minutes, or 12 seconds, there's about, we're getting almost no change because it takes time for that gas to diffuse out 1 meter. Then once we get to 1 meter's distance, once it's had enough time, the concentration starts increasing because we've kind of got the solvent front that's propagating outward through space in time. So hopefully you can kind of distill that and see what I'm getting at. I'm just looking for a qualitative description of what's happening in time that's different when you have a low diffusion coefficient or a 10 times higher diffusion coefficient. Basically, the curves are exactly the same numerically. It's just at what point in time are they the same numerically. So it compresses to the left, it peaks at the same, but it peaks faster. We have this period of time at the lower diffusion coefficient where we see no concentration. At the higher diffusion coefficient, if we zoomed in, we would see the same thing, but it would just be a lot shorter in time. Alright, that's enough of me talking. I hope you enjoyed this post, and I hope it's helpful for you to be able to complete your homework assignment.